Okay, so in a minute, we're going to be looking at solving polynomial equations where you have a degree bigger than 2. So that's the big idea. Okay, so with degree greater than 2. All right, so you already know how to solve this equation. It's a polynomial equation. You already know how to solve this equation. Okay, these are equations you've already had experience with. That one's degree 1, this one's degree 2. Okay, the degree tells you how many solutions to expect. Okay, so like the linear equation will have 1 solution, a quadratic will have 2 solutions. All right, the degree also is what we use when we begin naming them. So that's a linear and a quadratic equation. Okay. And you know how to solve a linear one, and you also learned how to solve a quadratic. Sometimes you factored, sometimes you used the quadratic formula. And then occasionally you could use the square root method. Those are the 3 ways we learned to solve a quadratic equation. Okay, so now what we're really going to be doing is solving equations like x to the third plus 8x squared plus 11x minus 20 equals 0. See how that one is degree 3. So it's going to have 3 solutions, and we could actually call that one cubic. Okay, and you could have degree 4, and that would be called quartic, and then sometimes we just call them polynomial equations. Okay, just all of these are polynomial equations. So some aren't so special, like if this were x to the 7th plus 4x to the 5th minus 3x squared plus 1. Let's do plus 4x minus 1. Okay, that one is degree 7. And at that point, I just call it a polynomial equation. I don't try to give it a special name, okay? All right, so what I'm doing in this video is kind of giving you the big idea of it, and then we'll go back and we'll look at one of the skills that you need to be able to do pretty quickly and easily. But the first video really gets at the overall idea and some of the vocabulary, kind of the steps involved, and then and goes through one example of the whole process. And then in another video, I'll go ahead and do a little more work with some of the skills needed to be able to do it, okay? All right, so let's go ahead and get started. And so let me start with this page here. So this is called Solving Polynomial Equations, and you'll see the blank notes were there for you to download if you wanted to, okay? All right, so first off, mathematicians for some reason think it makes things nice and easy when they use all this symbolic notation, but in reality, it complicates a relatively simple topic. So what they really mean, here's the example. They're really just trying to say f of x equals x squared plus 8x squared. Oops, I shouldn't have said squared. I meant to the third. Where's my pen on this? There we are. X to the third plus 8x squared plus 11x minus 20 is an example I'm going to use. And so when you're looking at a polynomial, to be a polynomial, the exponents have to all be positive or 0. Okay. The exponents have to not be negative. They have to be positive or positive whole numbers or 0. And what you see here out in front, that's what they're talking about with all those a sub n's, okay? So it just looks more complicated than it needs to be. All right, really only 2 of those terms matter anyway, okay? So like this first term right here, that's your leading term. And the a sub n part, that's the leading coefficient, okay, and then the n part right here, I wanted that to be green, it is, okay, that is the degree, and that is what tells you how many solutions to expect or how many zeros to expect, okay? Now, the only other term that gives us any information is this one at the end, and that one's called the constant term. So even though polynomials can have a lot of terms and be pretty messy, we don't really do anything with all of those. We really just look at the first one and the last one. And it tells us a whole lot about what to expect when it comes to solutions and what to expect if we were to graph it. All right, now the terminology will be kind of new. And so I want you just to hear it and then start getting used to it. And this part right here is important. I'm saying these different ways, these different words I'm going to use in these cases, that these are basically the same idea. The same thing. It's just what you might say, it's just semantics, okay? We can refer to the zero of a function, okay? And the k that I have here will be a number. So like I might say 1 is a zero of the function. The word zero you use when you're dealing with function and you have that function notation. So if I had written it f of x equals x to the third plus 8x squared plus 11x minus 20, I might ask you to find the zero of the function, okay? But that would be basically equivalent to me asking you for the root or the solution to the equation. See how now there's no function there, function notation there. It has it equal to 0. So it's written it like an equation. Then my terminology changes a little and I use the word root or solution. And so if 1 is a 0 of the function, it's going to be a root or a solution to the related equation. Now this is important. If 1 is a root or a 0, then x minus 1, we know, has to be a factor, okay, of the expression x to the third plus 8x squared plus 11x minus 20. So what I know is if 1 is a root or 0, then x minus 1 would have been a factor of that. And see, I couldn't have factored that in the normal way. I couldn't have used factoring by grouping and got it to work. So what I'm getting at here is these are just different ways of basically saying the same thing. It's whether you have function notation, whether you have it as an equation equal to 0, whether you just have an expression and you're trying to find if something's a factor. And then if 1 is a root or a 0, so if 1 is a real number like it is, then 1, 0 is going to be an x-intercept. So x-intercepts, this is what I want you thinking. X-intercepts, zeros, roots, and factors are all basically the same thing. They all are the same idea, okay? And so they would be x-intercepts of the graph of that if I were to graph it. All right, so remember I'm giving you the big overview here, and then we're going to go back and we're going to be breaking things down and doing more examples, okay? So my Word stopped working, so I'm having to use a different process for making my video, so hopefully it'll be all right with you. Okay. All right, so now we're getting into the actual process. So what happens is I have to find all the roots or zeros of a polynomial. And sometimes they give me a hint about ones that might work and sometimes not. And so the rational root theorem is something we'll have to use sometimes to get an idea of some nice numbers that might be solutions or roots to our equation so we can finish it up. and I just wanted to go ahead and put it on this like nice summary sheet right here. The possible rational zeros of a polynomial can be found by taking the factors of the constant term, the one at the end, divided by the factors of the leading coefficient. Okay, and we're going to do that with the example in a minute, so I'm not going to talk a whole lot about that here. All right, and then I wanted to put the steps out there for you, but this is what I really wanted you thinking about right here. The idea is this: find enough rational, that just means nice solutions, nice roots or solutions, so that you can get the polynomial broken down into just linear or quadratic factors, because then you set those equal to 0 and solve, and you know everything there is to know about solving linear equations and quadratic equations. So you're just going to break up your polynomial that has a degree 3 or more. You're going to break it up into polynomials that are degree 1 or 2, because you know how to solve those. Okay, so the steps are going to be to rewrite the equation so you have it as a polynomial equation equal to 0. If they didn't give you any hints as to numbers that might work, you're going to use the rational root theorem to get the list of possible rational roots. We're not going to do this one, but I included it because, you know, it is something that you could do that might save a little bit of time. Okay. And then we're going to use this process called synthetic division. I'm going to do a whole nother video just on synthetic division. It's a very easy process that you can get really fast at, and then you use it so much that you get the hang of it real quick. But we would use synthetic division to check which possible rational roots really do work. So instead of using long division, we'll be able to use synthetic division, which is a much quicker and easier process. And then once you have just linear and quadratic factors, you set them equal to 0 and solve the resulting equations, and they're just linear or quadratic equations, so you're really home free at that point, okay? All right, so now let's go and do an example from start to finish. One example, and then we'll do some more on another sheet. Okay, so here's the example we're going to do. So let me get through the first couple of steps, and then we'll do the last couple in another snip. So again, my Word document stopped working, so I have to do these snips here. All right, so here's what we're going to do. We're going to try to find the zeros, and I use that word because it was written with function notation of this function. This function is degree 3, okay? So there should be 3 zeros. Okay, so that means I need one nice one in order to be able to find the other 2. Okay. So you have to find at least one nice one, because then the remaining factor will be degree 2 and I'll be home free. Okay. So we're going to start, it says, by taking, since this was find the zeros, we go ahead and realize, well, that's really the same as me solving this equation. And they didn't give me a hint about what might work, so I have to use the rational root theorem to get the list of possible rational roots. And so if we do have something nice that's going to work, I know that it has to come from the factors of the constant term here divided by the factors of the leading coefficient. Okay, and the reason for that is because of what we've already seen happen with quadratic equations. I can explain more during our virtual sessions, but let me go ahead and just show you what it turns out to be. So the factors of 20 are 1, 2, 4, 5, 10, and 20. And it could be plus or minus on any of those. But then the leading coefficient this time is just 1. So that's plus or minus 1. Now, sometimes you have multiple numbers down in the denominator, and so you really get a considerably long list of possible rational roots, and you don't know which necessarily are going to work. And so it can give you a long list, and it feels like just way too much to deal with. But you get really good at this, very fast at finding the solutions. So there's my possible rational zeros. This is my list. Don't forget to do plus or minus, or that you could have plus or minus on those. All right, and then we're really not going to bother with Descartes' rule of signs. It's not that it's not useful, it's just that you can get by without it. So I made the decision to not bother you with it. But it can help you rule out maybe all the positive ones or rule out all the negative ones. Like sometimes it can save you time. So if you want to read about it, you can, but we don't usually make use of it. All right, so then we're going to wind up doing synthetic division to figure out which from this list really are roots, which from this list really do work in that equation, and then we'll be able to find the remaining two, okay? All right, so let me get a clean snip on this. I'm going to move it down just a little bit. So we're going to be doing, let's see if I can move that up. We're going to be doing steps 4 and 5 here. They kind of go hand in hand. Okay. All right, so here we're going to be using synthetic division to check which of the list of possible rational roots really were roots. Okay, this is using a process that you're gonna learn about in more detail in the next video. But here's the possible roots. That was our list. Okay, and so synthetic division is a process for determining which of those really works, and it's a shortcut for long division. So what goes in the box here will be the root. So if I'm testing whether 1 is a root or a solution, then 1 goes in the box. Then what goes next to it would be the coefficients on the problem that you're doing. So we were trying to solve the problem we were trying to solve was, let me jot it down over here, was f of x equals x squared, x to the third, plus 8x squared plus 11x minus 20. So what goes here would be the coefficients of these terms. So that's 1, 8, 11, and negative 20. So instead of doing long division, it's like you're just leaving the x's out of it. Okay? And so here's how the process works. I'm not going to explain it in gory detail here. I'll do it on another video. Bring down the first number, multiply, and write it right there. Every time you're going straight down, you're adding. When you're picking up the 1, you're multiplying. When you're adding straight down, get 20, then you multiply 1 times 20. And this is incredibly lucky. This doesn't happen very often. I wound up getting the remainder. This spot right here is where the remainder is located. And so this was 0. And if it turns out to be a 0, that means that 1 really was a root or a 0. And I can look at what's left right here, okay, to figure out what the remaining factor would be. Okay, so what the synthetic division is really doing, we don't always write this, is it's taking that original equation that we were trying to solve. And what that little process right there told me is that the 1 corresponds to a factor x minus 1. It tells me that x minus 1 for one factor, and then right here is the other factor. So see how it would have to be an x squared to get an x to the third? And it would be x squared plus 9x plus 20. Okay, is the other factor. So that's what that synthetic division did. Is it because I got a remainder of 0, it told me that x minus 1 was a factor, and then it also gives me the other factor. And we'll do more with synthetic division in the next video, so you'll get the hang of the process. Okay, but then once you've got it to where you only have linear and quadratic factors, okay, so if you know now this, then you can just set those equal to 0 like you did back when we were solving quadratics. And that second one, you can try to factor, And it's going to factor into x plus 4 and x plus 5. So you can continue factoring. And when you solve all of these, you're going to get x equals 1, x equals negative 5, and x equals negative 4. And so you just found all of the solutions. Okay? So the solutions would be the 1, the negative 5, and the negative 4. Okay? That would be your answer. Those would be the roots or the solutions to the polynomial equation. They'd be the zeros to the function. Okay? All right, so what I'm going to do in the next video is just go and look a little more at synthetic division and work through some problems related to synthetic division so you get the hang of that. Then I'll come back and I'll do some more examples on solving polynomial equations.